Hello everyone. My name is Carsten. I'm a researcher at Fraunhofer Institute in Duisburg, a microelectronic institute, and there I'm also product manager for our RISC-V microcontroller implementations that we call AI RISC, because we fine-tuned this RISC-V microcontroller to execute tiny machine learning or AI applications. And we are also a hardware institute, so we are building the chips. And today I wanted to show you or to guide you to the content of this small image processing box, where we have an image sensor and an FPGA that is doing some image pre-processing. And I will explain the use case to you and also have a short demo. But since it's just hardware, you will see a picture and a calculation that is done. So usually the problem is that customers wanted to have an application-specific processor for their needs. In some cases, battery-powered devices, so they need to be small and energy efficient, and therefore RISC-V is the optimal choice. So because we can fine-tune the ISA extensions and have hardware acceleration directly integrated into the chip, and at the end you will come up with some what we call ASIP, application-specific instruction set processor, either implemented on an FPGA or, if you want, on an ASIC. So in the project I will explain to you is called Amulus. It's an Eurostar project with two other companies, Traxasense and Advico. So during the last two RISC-V summits in Europe, we had shown some implementation details in posters, and I think the link to the posters you find in the explanation of this session. The idea there is to construct a new biomarker sensor based on laser spectral imaging. So the idea is shown here. You have a laser diode that somehow goes under your skin, and then with the blood in the veins, it somehow gets a spectral image, interference image that you can then monitor with some low-level CMOS imager chip or a specialized photo sensor that we designed within the project. But this spectral image needs some complicated algorithm to extract then the pulse rate, for example, or the blood pressure rate out of this spectral image. So therefore, it's necessary to have some on-chip data processing, and therefore we've chosen a RISC-V implementation. So this new concept is called SPG, shown here, spectral plethysmography. And in smartwatches today, you have a PPG sensor, and even in the hospital they are using this PPG sensor, but the problem there is that it's a cable most of the time in the hospital, but you have to go to the hospital. And within the project we wanted to have a new solution that is also portable and battery powered. So therefore we came up with a system approach. We split it in the first version that is available here and shown here. We split it the whole system into the image sensor, and then in the FPGA part we have the RISC-V system, which we can fine-tune to optimally compute the algorithm in the RISC-V processor. And since it's a research project, the algorithm is changing all the time. Therefore, FPGA was the right choice to adapt the hardware during the project. And we've chosen for the FPGA part low power and a small lattice FPGA, the ICE40. And the imager chip, which consists of a pixel array and also some interface to read out the pixel, and an LED controller to control the laser diode that is used to have this laser spectral image. We fabricated in XFAB 180 nanometer technology. Right now, it's been tested in the lab, and since it's using laser diode, we don't have a demonstrator that is eye protected or eye ready yet. But so therefore we've chosen a different CMOS image sensor. And the next generation that will be available in a few months then has the FPGA part, so the RISC-V directly integrated with the image sensor. And what we can achieve there is that we used a small RISC-V processor. We customized it to be able to calculate, for example, histograms that are needed for the algorithm. It just requires 4,400 Lutz in the small FPGA and can operate at 25 megahertz. And with this dedicated ISA extensions, we were able to speed up the calculation of the algorithm by roughly 4.5 times with only 300 additional lookup tables that are consumed in the FPGA, which corresponds to 6% of the overall FPGA area. So, and just a short demonstration of the system. Let's see. Where's the cursor? So, the light conditions are not that optimal here. So you have a lot of light and then also shadow. So as I explained here, we have an image sensor, grayscale image sensor, and the FPGA board connected to the image sensor. It takes round about every 15 seconds an image, and below you can see the histogram calculation that is done by this modified RISC-V. And what you will notice is if I block the light from this sensor, then the next histogram that is calculated here will only have black values. Let's say now it's stopped. Okay, so live demo is it worked several times, but but you get the idea. So that you can use a RISC-V to build a smart image sensor. Okay.